The follow-up example, the non-uniform rod or any other kind of situation that resembles that. It could be an orchestra where you have one portion of the orchestra is louder than the other portion of the orchestra. So we have lambda is equal to alpha x squared. What does that mean? Well, in this case, alpha is some constant which we're going to have to solve for. Okay, and then x squared means that it is louder on the two ends. So whatever speaker that is or orchestra, there's more sound being produced from the two ends, and it's proportional to the distance squared. So the sound intensity rises quite rapidly, and in the middle you have almost no sound intensity, because when x is 0, the lambda is 0, that means at the middle not too much sound is being produced, right? So it's going to be very similar again to examples that I did in chapter 25 for electric potential, right? So then how do we set up the integral? The beginning is similar to how we did it for the uniform one. We say di is equal to dp over 4 pi r squared, and then dp is equal to lambda dx over 4 pi r squared, and then we integrate it. Now at this point is where the difference comes in. The lambda is no longer uniform, so we can't pull it out of the integral, right? So we're just going to say I is equal to 1 over 4 pi, and then we're going to put the lambda function alpha x squared dx, right? And then if the point is at 0, 4, right, we can use the same r that we used for the uniform one, right? R, in that case, r squared was equal to x squared plus 4 squared, right? X squared plus 4 squared, which was 16, right? So we put here, and then we go -3 to 3. In this case, we can actually double it. You can go 0 to 3 and double it, because everything here is even. X squared plus 4 squared, x is even. This side of the rod is symmetrical to that side of the rod, to the left side. So then we should be able to double it. So then we just go here 0 to 3, double. X squared dx over x squared plus 16, right? So then we calculate that. So what is alpha? Why do we even need that? Well, alpha is a certain constant that we have to solve for in order to make the total power of the speaker equal to 100 watts, right? It's very similar again to the electric potential examples that I did, or electric field examples. Whatever constant that is has to be worked out and has to be calculated for. Well, we know the total power output of the rod is 100 watts, so we say here dp is equal to lambda dx, and then integrate it. In the previous case, I was able to pull out lambda from the integral, and then lambda was just equal to, we had p is equal to lambda L, and then lambda was just equal to p over L. So for uniform sound intensity, you can just simply do the total power divided by the total length, right? Here, since lambda is non-uniform, we actually have to put the function. So we have here p is equal to alpha x squared dx, then we integrate from -3 to 3, right? So then we can go 0 to 3 and double it on this one. So double 0 to 3 alpha x squared dx, right? Then total power of this the source is equal to 100 watts. So 100 is equal to 2. Then we can pull out alpha, and then integrate x squared dx. Well, the integral of x squared is equal to x cubed over 3, right? X cubed over 3. Then we go 0 to 3, right? So then we're going to have here 2/3 alpha, and then you have here 3 cubed, right? And then, of course, when you put in 0, you just get 0, right? So then you're going to have what? 2 alpha, and then one of the 3's cancels one of the 3's. You have here 3 squared, right? And then 3 squared is equal to a 9. And then, so that's equal to 18 alpha, right? So therefore, we can calculate alpha from there. Alpha is equal to 100 over 18. Then we can take that and we can put it into this alpha. So let's simplify that. Divided by 2 is going to be what? 50 over 9. So 50 over 9 goes into here. So that's the total sound intensity for the middle. Now convert that to decibels, then we can compare that to the previous case. Okay, so then you have dB is equal to 10 log of 0.37666 times 10 to the 12th. It's smaller or bigger than the previous case? Well, in the previous case, it was a uniform rod, and the answer in the middle came out, I believe, something like 116 decibels, so it came out louder. This one came out less louder a little bit, right? Why is that? Well, you can see that since the density is increasing, the sound intensity is increasing, so most of the end is the loudest. Most of the action is taking place there, right? Well, if you're in the middle, you're going to be farther away from most of the sound intensity, so you're going to be hearing a little bit less sound intensity than if the distribution of the sound source was uniformly distributed, right? So it should actually be a little bit less loud. So the answer makes perfect sense, okay? So now let's go to the end right here. How about that one? Should that be louder or not louder? Well, this one should be louder than the previous case, right? The previous case of if you were at the end, well, because you are really close to the loud portion of the music, right? So it should be louder than the previous case for the uniform sound intensity. Let's calculate that. Over 4 pi can come out, and then you have here lambda is equal to alpha x squared, and then dx over r squared, right? And then alpha can come out again, alpha over 4 pi x squared dx over r squared, and then the r squared, we can put down what the r squared was before. This one was 3 minus x, and this one was 4, right? So we can say integral I is equal to alpha over 4 pi x squared dx, and then r squared is going to be equal to 16 plus 3 minus x squared. So same as before, right? And then remember, we went negative 3 to 3. Good thing is that the alpha, we don't have to redo this integral because we've already proved what alpha needs to be in order to make the total power equal to 100 watts. So you don't have to recalculate the alpha, right? So alpha is equal to 50 over 9. 50 over 9, then we could put down what the 4 pi, right? And then we could integrate that. So let's go to the integral. Intensity in the middle, right? It's less than intensity in the middle, because why? You are farther away from most of the action here, especially you're farther away from the left side of the speaker, which also has a lot of action, right? So it's gonna, the end is gonna be definitely less loud than the middle, but it should be more louder than the end of the uniform rod. It's 7 decibels. So if you do compare them, you should see that it is louder than the end of the uniform speaker, right? Okay, how about this one here? 4 meters away this way. How do we set up that integral? That's right, 7 minus x quantity squared. Then you go from negative 3 to 3. Okay, and then alpha you put down 50 over 9. Okay, and then go to the integral again, right? So it is definitely, again, less intense than the end, the up here. Why? Because you are further away from the left side than the person over here, right? This person is closer to the left side than this person is 10 meters away from the left side. So the same arguments that we made for the uniform, right? Then we convert that to decibels. Interesting result comes out. So it's actually louder. The other one, the uniform rod, it was 112 decibels. This one was 113 decibels. So interesting thing is happening. So here, you are over here, you're really close to most of the loud action that's taking place here. This is loud, but this is also very loud, right? So it's a little bit hard to guess, well, which one is going to be louder, the uniform or the non-uniform? But if you really think about it a little bit more carefully, you can probably come to the conclusion that the answer does make sense. You are here 4 meters away from the very, very loud action, but you are 10 meters away, right, from the very loud action here, but this one overcompensates for it. So since you are very close to the very loud music, very loud source of sound, even though you're very far away from the other source of sound that's very loud, the left end, more than overcompensates for the fact that you are very far away from the left side of the rod, right? So the uniform rod, you are 4 meters away here, but the music is distributed uniformly. So no one piece of the rod is more louder than the other, but here you're very close to the very loud music. So that really kind of makes sense that this should be louder than this one. Okay, so now we're going to be doing other kinds of shapes of rod, maybe semicircles, complete circles, and also discs. Okay, thank you very much.